Okay, so my name is Dmitry Prohorov, and I'm from VTune Amplifier development team. VTune is a pretty famous profiler for performance analysis, software application performance analysis, and it's used like widely in different application domains, from HPC to embedded. And my responsibility in the team to make it relevant for HPC, performance tuning. And actually, okay. When we started this work, we tried to think from a user, from application developer perspective. So, what can they be interested in, right? And mostly, like when they develop their application, they'll introduce in parallelization, they put pragmas and measure performance, and very often it's not as expected, right? It's not linear and all that stuff. And mostly the questions are why my performance is not as expected of my parallel version, right? Or if this is okay for a particular hardware and I'm moving my application to for example, to a hardware with more number of cores, so why it's not scaling? And you know that we tried, to decompose these questions in terms of OpenMP. So first, it's important to know, so what's the fraction of serial time when you parallelize with OpenMP, right? Because serial time will limit scalability of your application further, and on particular system and further. And what is the efficiency, parallel efficiency of your parallel part? What theoretical gain can I have, for example, if I invest in performance tuning of this parallel part of my work, right? And if I introduced like several lexical regions, so what region is less efficient, how much theoretical gain I have for a particular region, and what I can do with this. So I have some clauses like, for example, scheduling, I don't know, with some granularity. I might collapse my loops and all that stuff, but what can I do? And if profiler is not OpenMP aware, so OpenMP unaware, so usually you are puzzled with this. So this is how you see like a hotspot analysis in VTune when it was OpenMP unaware. Like you can see hotspots with all that stacks, with all that OpenMP internals, and you might not be able to recognize to answer to the questions we just articulated, right? So what we did in VTune. So this is a typical summary view when you profile OpenMP application in VTune. So you have clear articulation of serial time fraction with percentage of elapsed time. We have like parallel time and how much potential gain you can actually have if you eliminate inefficiencies, different kind of inefficiencies that you have in your parallel, like in your parallelization with OpenMP. And the breakdown of this theoretical gain by OpenMP construct, lexical construct that you introduce in your code. So, looking at this picture, you can see pretty clear what's the fraction of serial code, and if you can benefit from further tuning of your parallel part of your code. Probably everything is okay here and here, and you will need to look at, for example, architectural efficiency or something else, but not in like OpenMP efficiency. Okay, let's look at the metrics actually. So this is like an instance of a parallel region. And here in green you might have efficient time, the time that is actually spent in your application code, doing useful work. You can have imbalance, so where, for example, worker threads can spin, waiting for other threads on a barrier construct, right, but they do nothing. So they just burn in CPU without any useful work. You might have, inside a parallel region instance, you might have other inefficiencies, like if you do locking, you might have like spin locks there, right? Again, so not useful work. You might have, for example, scheduling. If you do some dynamic scheduling to eliminate OpenMP balance, so then scheduling also is not for free. You might have like, if you have a lot of parallelization small instances like microsecond instances, you might have overhead for work forking, right, for each of them, the instance. You might use atomic operations that are also not they are lighter than like critical sections, but they're not free. And what we can do, we can calculate this and then normalizing this by number of threads to show the gain in terms of elapsed time. Because if we like show metrics in terms of CPU time, it might be difficult, to understand the performance in elapsed time. For example, on many core systems, when you might end up with more than 200 threads, what is like imbalance of like 2 seconds. So if you eliminate this, you might have like just 0.0 like 2 seconds of the benefit. If you have just 4 cores, you might have 0.5 seconds of benefit. This is different, right? So it's important to show the metrics in the elapsed time. And so here, if we normalize them, so we can show the time of inefficient time in terms of elapsed time and classify it by different categories. So because tuning strategy will depend on what particular inefficiency you have. Like for example, if you have locks, you might want to eliminate locks with reduction, doing reduction, right? For example, or if you have scheduling, you might play with chunking to make like iterations like more coarse grain and eliminate scheduling overhead. If you do a lot of work forking, so probably you need to look at moving from like parallel regions to work sharing constructs from OpenMP parallel 4 to OMP parallel and inside OMP4 constructs, and so on. So in VTune we use tracing. So currently we support, so this methodology is supported by Intel OpenMP runtime. We do some tracing, but we do tracing of global points, forks, joins, barriers. We try to eliminate per thread instrumentation because it might hurt performance, overhead, especially on many core systems where you can end up with more than 200 threads, for example. Actually, we're looking at OMPT interface that was just articulated in the previous talk. And actually, we are working with John Miro Krumey, actually to enhance it with some callbacks to eliminate per thread instrumentation to get important performance metrics like, for example, imbalance. It's in the process. And some statistics we are based on sampling technology. Because, like for example, to measure scheduling overhead, and if you want trace scheduler, you will hurt it, and the performance of like for example, the elapsed time of your application under profiling might will be increased in several times. So we mix tracing of global points like fork and joins and barriers with sampling information. Okay, in VTune. We have so-called analysis types that are actually focused on particular performance aspects. Like, for example, Hotspots, mostly for logarithmic analysis. We have general exploration for microarchitectural issues. We have memory analysis to see efficiency of memory accesses. And we introduced HPC performance characterization analysis that you can choose from the GUI or you can use in command line. And after, running the application under this analysis, you will have the summary page that's with like CPU utilization section that mostly will show you the OpenMP analysis. So here again, so you will look at serial time, at parallel region time, and the potential gain that you can have like investing to this tuning. Like for example, here you have like 17.6% of theoretical gain from elapsed time. So if you think that it's worth to look at this, then you can look at particular lexical constructs actually that you are introducing, right, like parallel regions, to see what construct is more inefficient to look at further. And in more detailed view, like grid view, so actually, yeah, if you press on the parallel region in the summary, you will go to grid view, and here you can see like parallel regions and barrier constructs. You can expand them by barrier constructs, and here you can see the rows that are like classified by particular inefficiencies, like imbalance, lock contention, like work forking, scheduling, atomics, and so on. And here we have CPU time normalized by number of threads, so it's like in elapsed time. For example, here you have like four seconds of imbalance, like in terms of elapsed time, and if the imbalance time is pretty big for this barrier construct, so probably you need to look at dynamic scheduling. Of course, cautiously, because it might be not so cache friendly, right? That static scheduling, but in some cases it might work. And for example, here I used and you can look at some loop attributions here, like static number, like loop chunk, and the loop iteration count. And for example, here I used like dynamic scheduling straightforward with default chunk that is 1. And the next thing that I, after like next run, I see that okay, imbalance right now is vanished, right? It's good, but scheduling overhead is worse, right? And actually, it's not just scheduling overhead. Since dynamic scheduling is less cache friendly, the elapsed time will be even worse. So then you need to play with chunking. You can see that like loop chunking is 1, like dynamic 1. So you need to play with chunking to have more coarse grain work to eliminate scheduling overhead. And actually, also recently we added ability, to see serial hotspots. So these are hotspots. These are like functionality that is done outside of parallel regions. Sometimes you cannot eliminate this, but sometimes probably you can look at opportunities to parallelize more. And here, on summary view, you can see like top serial functions right away, and function/loops. And probably you will, like for example, here I have like mini-FE application, and I have a loop. So probably this is just a initialization phase, but still this loop like occupies particular like amount of application time, right? And probably you need to you have ability to parallelize it. Also, you can see more details in the grid view. If you expand serial time and master thread, so the work is done serial work is done in master thread. You can see like more like functions here, not just top 5 but more, and with some more metrics here. And if you want, for example, to eliminate the warm-up time, you can, in grid view, we have also timeline. You can just filter by a timeline region and see these metrics, for example, for the computational part of your application. Filter it by. Okay, what else? Actually, we also have we call it scalable representation of a timeline. For example, here I have a picture with application that is run on Intel Xeon Phi machine node with like 288 threads. And the green part, this is like useful work. This is the work that is done in in application. And the black holes means that there was no actually useful work there. It might be spinning in on barriers, or I don't know, on for example the logs, any. And on the ruler you also will have the region marks that correspond to a particular instance of OpenMP construct. So if you zoom in, so you will see these region marks, and mostly this view is just to have a bird's eye view, or you can expand it, zoom it, to see some patterns of your application behavior. So, for example, if you have some like imbalance on a barrier, so you will see at some point you will see like black hole execution here, and probably you will recognize the patterns. But this is just a, I think, complementary view. Mostly, since application can invoke parallel constructs millions of times, right? Sometimes it's not very efficient to look at particular instance on timeline. So rather, probably you might want to look at aggregated metrics by a lexical construct, right? Because if you put a lexical construct, you can tweak like clauses like for the whole runs, right? For the whole run, rather than tuning for particular instance. Okay, and actually also we have ability, if you like double click on a particular region name in the grid, then you can drill down to source view, and then VTune will show you your parallel construct positioning on the pragma here, and with some metrics that are, like for example, CPU time by the source lines that were executed in this particular region. So this is just a, I don't know, quick navigation. And actually, if you double click further, some like editor will be invoked, and you can even, for example, if you have an editor register it on Linux system, so it will be automatically picked up, and you will have the source there, and you can change the source and recompile even just in the tool. I mean, in the tool flow. Okay, let me summarize. And yeah, before summarizing, also let me say that actually we apply the same concept for hybrid applications, MPI plus OpenMP. The metrics are the same, but for MPI we can recognize also, MPI speeding through sampling, and we will show OpenMP metrics for a rank that actually was on the critical path of OpenMP communication. Of MPI MPI communication. Like the less rank is spinning, the more it's on the critical path. And so we will show these metrics by the MPI rank of choice that is on the critical path. So you will be able to assess pretty quickly OpenMP efficiency for your MPI plus OpenMP for hybrid application, right? So to summarize, in VTune Amplifier we have, together with Intel runtime, OpenMP runtime, we have ability to show OpenMP efficiency metrics, like on OpenMP language, on the language of pragmas, clauses like schedule, right, chunking, and all that stuff, to allow a user to understand what can be changed with the application to make it more efficient in terms of parallelization. The analysis actually is well scalable on many core systems, because we use not just tracing, we have combination of tracing that we do by global points and sampling technology. And having these two technologies combined allows us to avoid a lot of overhead that collection might bring, even on many core systems where you can have potentially more than 200 threads. Yeah, as I said, OpenMP analysis is MPI aware, so it's used for MPI plus OpenMP applications. The full feature set, including, for example, serial time hotspots, is available in the latest VTune Amplifier XZ 2018, and that is available standalone and also as a part of Parallel Studio XZ 2018. But actually, you can even try earlier version, but they might be miss some features. And also, I can say that right now we also ship a tool that is included in VTune that is called Application Performance Snapshot, that gives you like high overview by the whole application, by important aspects for HPC analysis. MPI time, OpenMP imbalance, memory access efficiency, and flop analysis, some flop analysis. And we use the same instrumentation from OpenMP there. And the tool shows you like OpenMP serial time and OpenMP imbalance. So you can, and the application performance snapshot included into VTune. But it allows you very quickly see the important metrics by the whole run, not waiting for the result processing that you might need for detailed information that VTune shows. Okay, so thank you for listening. And if you have any questions,